So now that we have this microscopic model, right, a bunch of balls bouncing around inside of a container of some sort, we'd like to relate this to something macroscopic, something we can actually measure. And so the thing to start with is pressure. Because if we think about our model, right, we have a box, we have a bunch of gas particles bouncing around. At this microscopic level, what causes pressure? I'd like you to pause and think about that. Pause the video, answer that question for yourself, just write some notes to yourself, and we'll talk about it. Okay, I hope you had the chance to pause and think about this. What causes pressure? Well, these gas particles are all moving around and hitting each other. And remember, pressure is a force exerted over an area. So in this case, what's exerting the force and what's the area? The force that's being exerted is from the collisions of particles with the walls. So the pressure is exerted on the walls of the container. And that's what causes pressure. So, right, all these things hitting the wall and bouncing off, that pushes on the wall, and what you have is a bunch of these, right? You have billions and billions of these particles hitting at a macroscopic level, right? On something like us, right? We have pressure being exerted on us all the time by the atmosphere. We just don't notice it because we're constantly feeling it. But you do notice a difference if you go higher pressure in water, for example, or lower pressure if you go up into the mountains. Okay, and so our pressure is equal to a force over an area. And if we can figure those out, we can find the pressure from our model that we have of all these random particles moving around. So we'll just look at one particle to start with to keep things simple, and then we'll scale that up, right? Once we've done it with one, all the other particles will behave the same, and we can just add together all the different particles that we have to get the total pressure. Okay, so I've drawn a two-dimensional box here, but of course all this is happening in a three-dimensional area. So this is sort of our model with our single particle here. So we have a box with 3 dimensions. We'll define this dimension as the x dimension, and our box has specific dimensions as well. So we'll say it has the length of a in this dimension, a depth of b in this dimension, and a height of c in this dimension. And we'll make our gas particle blue. Right, so here's our particle. And we're just thinking about one. Of course, actually there's going to be, a mole of these or whatever. But let's imagine it traveling towards this face of this wall here on the right-hand side. That's the wall of our container. We'll get to the other walls, but we're just going to think about one wall at a time. And we have our gas particle. We're going to call it gas particle number 1, because we're going to add together results from a bunch of these gas particles. So if we take particle 1, we'll call the velocity u. This is the variable that's used in your textbook, so I just want to be consistent with it. So this is a velocity. And a velocity, as you remember, has a direction. And so let's think about the velocity component in the x direction, right? So it could be moving up and down, but we just care about the left and right motion when we're thinking about the right wall. Because if it moves up, it won't hit the right wall, right? So we just care if it's moving in the direction of the x direction. Okay, now if we're thinking about area, because we need that as part of our calculation here, if we're looking at just the right wall, the area of that wall is equal to b times c, right? Whatever those distances are. So that's easy. We've already taken care of that. So now what we need is the force that is exerted on that area. Now, force, we said that these particles are obeying Newton's laws of motion. So we can say, okay, force is equal to mass times acceleration. And that would work for this, but a slightly more, well, I don't know straightforward, but a slightly easier way with this particular way of thinking about this is another way of writing force is that it's a change in momentum over time. So P, this is momentum, which we give the symbol P, which is equal to the mass times the velocity, right? And so this is a different way of writing Newton's second law that is exactly identical to force equals mass times acceleration. Right? Acceleration involves time as well. This is just, it can be more useful to consider it in this way. So let's think about, we know that this particle is going to, this blue particle, we'll use the rainbow color here, it's going to travel along, hit the wall, and bounce off, right? And so what we want to know is how much force does that exert? Right, and so to get that, according to this version of Newton's second law, we need to know what's the change in momentum. All right, so let's think about our particle coming in and hitting the wall. So our blue sphere here is coming in with u1x. Now it can be coming in even at an angle, and that's fine. And it bounces off, and because we assume everything is an elastic collision, so the ball's not springy, it won't absorb any energy from the wall, it'll just bounce off. It'll come off at the exact same speed, just in the opposite direction. So the x component will stay the same, just change sign. So if we think about what's the momentum before, well, it's the mass of particle 1. We'll just call it m. We'll assume we have all the same kind of particles here, times our velocity beforehand. And after it hits the wall, it's just going to be the negative of that. So what is delta p? Well, it'll be 2 mu1x. Right, because you just take p before minus p after. And that'll give us 2 mu1x. Okay, so we got the delta p, and then the question is, what is delta t? What's the time scale over which this occurs? We just need to think about the x direction. We can ignore the other walls, and we know the speed that or I should say the velocity at which the particle is moving back and forth between the left and right walls. Right. So our particle is just going to be bouncing back and forth because we're ignoring other particles. We assume nothing else is there. Right. So the velocity of the particle is defined as distance over time. This is probably bringing back lots of memories of your physics classes that you've had, hopefully. And we know that this overall distance here is a. Just by definition, that's how we defined our box. Okay, so we can rewrite this equation to solve for time, this equation right here, and say that time is equal to distance over velocity. So if we know how far the particle is traveling, which in this case, we want to know how long it takes to hit the right wall again after it's hit it the first time. So it'll travel a distance of 2a, so because it'll hit, go back, bounce off the left side, which we're not counting at this point, and then it'll come back again and hit the right side. So it's going to go 2a distance, and we know the velocity. It's u1x, right? It's traveling at that velocity. So then now we found the force. The force is equal to delta p over delta t, which we found delta p is 2m u1x. Delta t is 2a divided by u1x. All right, so we'll get our 2's will cancel, and we'll get m u1x squared divided by a. All right, this video has gone on long enough already, but in the next video we'll look at taking that force that's applied, we know the area, and finding what's the pressure.